Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we're going to review the reactivity of the alcohol functional group. And hopefully in the video I'm going to simplify how alcohols actually behave. Now, if you haven't done so already, I do suggest you watch the following before watching this video. Recognizing nucleophiles, bases, electrophiles, and acids, the SN2, SN1, E2, and E1 video, as well as the organic chemistry reactions problem-solving process video. That being said, let's get on to alcohols. The image that you see here is a summary of all of the components of the alcohol functional group and how each of those components behave. Unfortunately, an image like this is not likely to be found in any organic chemistry textbook or any organic chemistry class. It's a compilation of everything that I've learned about alcohols, all in one place. We're going to start with the oxygen, and notice that you have two lone pairs on the oxygen. Typically, if you have lone pairs on something, that is going to signify that it is at least a weak nucleophile and a weak base. OH is considered to be a bad leaving group because it's too basic. However, because it is a nucleophile and a base, the oxygen can attack strong acids and electrophiles to transform itself into a good leaving group for subsequent dehydration or substitution reactions, or it can get turned into a protecting group, which we won't cover in this video. Next, let's look at the hydrogen that's bonded to the oxygen. This hydrogen is a weak acid. Alcohols tend to have a pKa of about 16, which means that if we're going to remove this hydrogen in an acid-base reaction, we need a fairly strong base to do so. Some good options are sodium amide or sodium hydride, so NaNH2 or NaH. When the hydrogen is removed in this acid-base reaction, it will leave behind a strong nucleophile, known as the alkoxide anion. Beyond that oxygen and hydrogen, we'll move on to the alpha carbon, the beta carbon, and the beta hydrogen. If we turn that OH group into a good leaving group first, you'll see that these alcohols end up having a lot of the same functionality as alkyl halides. That is, we can undergo SN2, SN1, E2, and E1 reactions with them at all of those respective sites at the alpha carbon and with those beta hydrogens. That makes learning a lot of the reactions of alcohols a lot simpler because it just builds upon knowledge that you already have from your study of alkyl halides. Now, there is one additional reaction that alcohols can undergo that the alkyl halides do not, and that is that the alpha carbon is oxidizable as long as it's bonded to at least one hydrogen. So in other words, primary and secondary alcohols can be oxidized. That being said, let's move on to all of the individual reactions. As mentioned in the previous slide, the hydroxide ion is a bad leaving group because it's too basic. Therefore, alcohols don't typically behave like alkyl halides unless we can transform that OH into a better leaving group. Luckily, we can do that because the oxygen is nucleophilic and basic because it has those lone pairs. So there's two ways we can turn that OH group into a better leaving group. First, we can attack an acid. And when we attack an acid, the oxygen will accept a hydrogen, giving it a +1 formal charge, and that turns it into water, which is not very basic at all. So now it can be a good leaving group. The second way is that we can attack an electrophile. So while it is possible for the oxygen to end up with a +1 formal charge to become a good leaving group when it attacks an electrophile, other times the alcohol's hydrogen is also removed in a subsequent step. In those cases, the oxygen can still be a good leaving group because the charge on the anion might be stabilized in some other way, such as through resonance. The first reaction of alcohols we're going to look at is dehydration with acid. Now, dehydration is really just an elimination reaction. Because the mechanism involves beta elimination, we're going to need a strong acid that has a non-nucleophilic or a big and bulky conjugate base. Two examples are sulfuric acid and p-toluene sulfonic acid. You can see them there. On the right-hand side of the page, you can see their conjugate bases, and you can see that next to that negative charge on the oxygen, we have a big, bulky group. That means that it cannot act as a nucleophile, it can only act as a base. So using our organic chemistry reactions problem-solving process, let's figure out what the product of the reaction on the bottom of the page is. The first step of the problem-solving process, of course, is to write down everything we know about the first reactant, and then the second step of the problem-solving process is to do the same for the second reactant. So the first reactant there is a primary alcohol, and from a few slides ago, we know that there are three very important things that we should make a note of with primary alcohols. First, there are lone pairs on that oxygen, which means that it can attack something as a nucleophile or a base. Second, we have at least a weakly acidic hydrogen. And third, because this is a primary alcohol and there are hydrogens on that alpha carbon, we can oxidize that alpha carbon as well. When we look at H2SO4, we know that that's sulfuric acid, a strong acid. Now that we've written down everything we know about those two reactants, we should look for anywhere where there's overlap, where we can figure out what at least the first step of this mechanism is. And I'm noticing that we have a base and a strong acid. So the first step here is going to be an acid-base reaction. So I'm going to draw in the lone pairs on the oxygen, and I'm actually going to rewrite H2SO4 in a different way to emphasize that it's acidic. So I'm going to write that as HOSO3H. In chemistry, we always draw arrows from the most negative region to the most positive region. So I'm going to take that lone pair and I'm going to attack that acidic hydrogen. That, of course, is going to break this oxygen-hydrogen bond, and that oxygen on H2SO4 is going to receive those electrons. Once we have the intermediates drawn, you'll notice that we have a primary protonated alcohol. In other words, that oxygen gained another bond to a hydrogen and now has a +1 formal charge. Now I have a note above this reaction that says primary protonated alcohols dehydrate via an E2 mechanism, while secondary and tertiary protonated alcohols dehydrate via an E1 mechanism. So we can go back to the problem-solving process here and write down a couple of notes on that primary protonated alcohol in order to figure out what to do next. Because we just protonated that oxygen, now we have H2O instead of OH as our leaving group. And H2O is a very good leaving group. We still have an electrophilic alpha carbon because it is bonded to an oxygen. And we know that we have an elimination-prone beta hydrogen on that beta carbon. Now, we already mentioned that we can do an E2 when we have a primary protonated alcohol. And in a future slide, I'll go over why we can also do an SN2. So we can do an E2 and an SN2 reaction with this. So now that we have that, let's talk about what we have with OSO3H minus. Well, on this slide, I mentioned that this conjugate base is a non-nucleophilic base. And as a non-nucleophilic base, we know that it can only attack hydrogens, and it cannot attack an electrophile because it's non-nucleophilic, which means that, as a base, it's only going to do an elimination reaction. So now we can look at the overlap between the two reactants here, and I see that we can do an elimination reaction with the non-nucleophilic base, and we can do an E2 reaction with the primary protonated alcohol. So that's what we're going to do. So whenever we do an elimination reaction, we have to draw the beta hydrogen that we're going to eliminate. So I've drawn that in blue, and what's going to happen is the negative charge on this non-nucleophilic base is going to come over and attack that hydrogen. That's going to break the carbon-hydrogen bond, and the electrons from that bond are going to form a double bond between the beta and alpha carbons. Of course, that's going to put too many bonds on that alpha carbon. That'll be 5 there. So at the same time, we also need to have the leaving group, water, leave. And of course, that is going to give us our product, which is simply going to be an alkene, CH2, CH2. We'll also get a water byproduct, and we get back our original acid, our acid catalyst H2SO4. Hopefully what you can appreciate here is once you start learning about alcohols, you can start to see that you already know every individual reaction that goes on to get from the starting material to the product. What a lot of students try to do is memorize every reaction that they see. And this is a big mistake because there are hundreds or even thousands of reactions that you'll encounter in organic chemistry. So with alcohols, simply going through the problem-solving process, you realize that this is just an acid-base reaction first, which is really easy, and then an E2 reaction, one of the first ever reactions that you learned in organic chemistry. In our next reaction, we are going to carry out a dehydration without acid. Sometimes in situations where acids would not want to be used, the dehydration can still be carried out using phosphorus oxychloride, an electrophile, and pyridine, a base. This dehydration always occurs via an E2 mechanism. So I want to clarify that when we have a protonated alcohol, it depends on whether it's primary or if it's secondary or tertiary. Here, when we use phosphorus oxychloride and pyridine, it's always going to be an E2 dehydration no matter what. So let's figure out the product of the reaction at the bottom of the page by going through the entire problem-solving process. So once again, we do have our primary alcohol, and everything we said before about the primary alcohol is still true. We also have the electrophilic phosphorus, because the phosphorus is bonded to 4 different electronegative groups, making it partially positive. So when we see this, we know that we can attack the phosphorus with the nucleophilic oxygen. So we're going to draw our arrow from our lone pair on the oxygen to the phosphorus. So let's go ahead and draw this. So we have POCl3. And the lone pair on the oxygen is going to attack the electrophilic phosphorus. And when it does so, it's going to kick off a chlorine, much like an SN2 reaction. When we add on that POCl2 group, this hydrogen on the oxygen becomes a lot more acidic due to resonance stabilization of its conjugate base. So that means that pyridine, which I'll just abbreviate PYR, with a lone pair, this pyridine is simply going to come in and do an acid-base reaction and remove that hydrogen, giving us the intermediate that's shown here. Let's analyze this intermediate. We have OPOCl2, which is a good leaving group, and it's a good leaving group because the negative charge on that oxygen is going to be very well stabilized through resonance. We also mentioned that whenever we use POCl3 and pyridine on an alcohol, we're going to get an E2 mechanism. So we should also mention that we have elimination-prone beta hydrogens. So here are the notes that I have on this intermediate. So what base are we going to use in order to remove that beta hydrogen? Well, we're simply just going to use another equivalent of pyridine. So when we draw in our next step, we're going to use pyridine again. And, of course, we'll draw in one of our beta hydrogens. And we're going to draw an arrow from our negative to our positive, removing that hydrogen. The carbon-hydrogen bond once again breaks, and we put a double bond between the alpha and beta carbons. And as a result, we have to kick off this leaving group. So once again, we're simply going to get an alkene, which is going to complete our dehydration or our elimination. The next set of reactions we're going to cover are how to convert alcohols to alkyl halides via a substitution mechanism with and without acid. Let's look at with acid first. So alcohols can be protonated by the strong acids HX, where X is chlorine, bromine, or iodine. And once we protonate them, they become good leaving groups. Then the halide nucleophile, or the conjugate base of HX, will then react with the alpha carbon via a substitution mechanism. Primary protonated alcohols substitute via an SN2 mechanism, while secondary and tertiary protonated alcohols substitute via an SN1 mechanism. I do want to point out that HCl cannot be used to convert a primary alcohol to a primary alkyl chloride without the presence of a catalyst such as ZnCl2, as the chloride anion is not a strong enough nucleophile to react via the SN2 mechanism. However, HBr and HI are able to be used without an extra catalyst to convert the primary alcohol into a primary alkyl halide. So let's analyze the reaction shown on the page right here. Once again, we have an alcohol, except this time it's a secondary alcohol, not a primary alcohol. However, the fact that there's a nucleophilic and basic oxygen, an acidic hydrogen, and an oxidizable carbon still remain. When we look at the second reactant, we of course have a strong acid. So once again, looking at where we have overlap between the two reactions, we have a basic oxygen with a strong acid. So of course, we're going to draw an arrow from our lone pairs on the oxygen to our hydrogen on the acid. That of course is going to break this hydrogen-chlorine bond, and the chlorine will accept 2 electrons. That's going to give us a secondary protonated alcohol, and based on the information already presented in this video, we know that we can either do an E1 or an SN1 mechanism when we have a secondary protonated alcohol. Of course, for either of these reactions, the first step is that the leaving group is going to leave. So we're going to have the leaving group leave here, and what this gives us is it gives us a carbocation in this secondary position. And anytime you have a carbocation, it's crucial that you check and see if you can do a carbocation rearrangement and make it a more stable carbocation. So in this case, we actually do have an adjacent tertiary hydrogen that we can do a 1,2 hydride shift with, and that is going to give us a tertiary carbocation. Once we have the tertiary carbocation, now we can show the last step of this reaction, which is, of course, we have that Cl negative nucleophile, and this is simply going to come in and attack that carbocation, giving us our final product, where we have the chlorine in that tertiary position. Once again, I want to point out that there isn't any new reaction mechanisms associated with the reactions of the alcohol so far. All that we're doing is protonating the alcohol first to make it a better leaving group, and then we're using reactions that we've already learned about, the SN2, the E2, the E1, or the SN1, to simply complete the reaction. Alcohols can also be converted to alkyl bromides or alkyl chlorides without acid in the presence of either phosphorus tribromide or thionyl chloride with pyridine, respectively. For these reactions, the substitution mechanism is always going to be SN2. Therefore, tertiary alcohols will not undergo these reactions. You can see that phosphorus tribromide has a phosphorus that is electron deficient. So the phosphorus is an electrophile. Same with thionyl chloride. That sulfur is very electrophilic. So when we go to these two reactions on the bottom of the page, we simply need to note that we have a nucleophilic and basic oxygen, and that we have an electrophilic phosphorus or an electrophilic sulfur. With the first two steps of the problem-solving process, I'll get the following notes. In this first reaction, I can see where the overlap between the two reactions is. I have a nucleophilic oxygen, and I have an electrophilic sulfur. So of course, when we go to draw the mechanism of this, we're going to draw an arrow from the lone pairs on the oxygen to that electrophilic sulfur. When we do that, that is going to kick off one of these chlorines, and that's going to give us our next intermediate. Now we have this OHSOCl. Pyridine, which has a lone pair, is going to come in and deprotonate that OHSOCl group, putting a lone pair back on this oxygen. In these two steps, we turned OH, which is a bad leaving group, into OSOCl, which is a great leaving group. So now that chlorine, which we kicked off in the very first step, that Cl- is simply going to attack this electrophilic carbon and kick off this OSOCl leaving group, giving us our SN2 product right there. In the bottom reaction, one of the lone pairs on that oxygen is going to attack the electrophilic phosphorus in PBr3, and of course that is going to kick off one of those bromine leaving groups. That's going to give us this OH PBr2 group, which is a fantastic leaving group. So now we have Br negative, which was just kicked off in the previous step, and this is going to act as our nucleophile, and it's going to do a backside attack at this carbon, which is going to kick off this OH PBr2 leaving group. That, of course, is going to invert the stereochemistry as an SN2 reaction and give us our bromine on a dash. And once again, you can hopefully see the parallels between the steps in these reactions with reactions you already know. The next reaction that we're going to learn is how to convert an alcohol to an alkyl tosylate. TSCl, shown on the right, has an electrophilic sulfur that can be attacked by the oxygen of an alcohol. This will turn the alcohol into a good leaving group, OTS, called a tosylate. The tosylate is not a good enough leaving group for the chloride anion to react with it, so alkyl tosylates can be isolated and used in other reactions. So let's go ahead and take a look at what we have here. We have that OH, and we know that it has the nucleophilic and basic oxygen, and we just said that that sulfur is electrophilic. So as usual, we're going to draw an arrow from our nucleophilic oxygen over to that sulfur. So I'm just going to draw the arrow to this TS, which is just an abbreviation for that tosylate group, and of course that's going to kick off that chlorine. That's going to give us this OTS group, and of course we still have that hydrogen for right now. In the next step, the lone pair on pyridine is going to come in and remove this acidic hydrogen on the OTS. This will give us our product, the alkyl tosylate. When we isolate the alkyl tosylate, we can react it further with a strong nucleophile in an SN2 reaction or a strong base in an E2 reaction. In other words, we would get a nucleophile in place of where the OTS is, or we can get an alkene when we kick off that OTS leaving group in an elimination reaction. So we've covered a lot of reactions so far with alcohols, taking advantage of the nucleophilicity and basicity of the lone pairs on the oxygen. It can seem a little bit overwhelming at first, but when you break it down, really all we're dealing with here are SN2, E2, SN1, or E1 reactions. So on this slide, we're simply going to review which of those reactions we end up doing. When we have a first degree or primary protonated alcohol, and we react that with either a non-nucleophilic base or a halide, we're always going to get one of the twos. So in other words, if we use the non-nucleophilic base, we'll get an E2. If we used the halide, we would get an SN2. Now that changes for secondary and tertiary protonated alcohols, in which case, when we react those with a non-nucleophilic base or a halide, we are going to get either an E1 or an SN1 reaction. When it comes to the primary and secondary alkyl tosylates, we can react those with either a strong nucleophile or a strong base. And those will always give us SN2 or E2 reactions. Now, as you hopefully remember, when you have a tertiary leaving group, you cannot do an SN2 reaction because there's too much steric hindrance. So a tertiary alkyl tosylate can only be reacted with a strong base to do an E2 reaction. When you have primary, secondary, or tertiary alcohols, and you react those with POCl3 and pyridine, the only reaction you're going to do in this case is going to be an E2. And finally, when you have methanol or a primary or a secondary alcohol, and you react that with either SOCl2 with pyridine or with PBr3, that is always going to be an SN2 reaction. To this point in the video, we have really just focused on the nucleophilicity and the basicity of the oxygen being able to attack a strong acid or electrophile in order to turn that OH into a better leaving group. Now we're going to focus on the acidic hydrogen on that alcohol. Because it's only a weak acid, we can use a strong base, such as sodium hydride or sodium amide, to deprotonate the alcohol. Of course, that's just an acid-base reaction. Deprotonation of the alcohol will generate something called the alkoxide anion, which is a strong nucleophile, which we then, of course, can use in other reactions. So let's take a look at this two-step reaction on the page here. I've already taken care of the first step of the problem-solving process with my notes below the alcohol. So now I'm going to look at that NaH. And NaH is, of course, an ionic compound, Na plus and H negative. And H negative is a very strong base. So, of course, what are we going to do? Well, we look for the overlap, and I see a strong base and an acidic hydrogen. So I'm going to cross out my Na, and I always like to say, whenever you see Na, you say, oh hell nah, and you cross it out, and you draw a negative charge on whatever it's bonded to. So I have my negatively charged hydride anion, that's my strong base, and this is simply going to remove the hydrogen from that oxygen. That oxygen-hydrogen bond is going to break, and we're going to get a lone pair on that oxygen. Of course, that is going to give me this, which we call the alkoxide anion. The alkoxide anion has lone pairs and a negative charge. So this is actually going to be both a strong nucleophile and a strong base. So what we're doing here is analyzing this as if we were doing the first step of the problem-solving process again, because we have a second step in this reaction. As a strong nucleophile, we can do SN2 reactions, and as a strong base, we can do E2 reactions. And of course, now we're going to look at the second reactant on that line, and this looks like a primary alkyl halide. And of course, when we have primary alkyl halides, we can make our notes on those, but essentially, for shorthand, they are susceptible to SN2 reactions and, to a much slower extent, E2 reactions, so I'll write that really small. So now what we're going to do is we're going to look at the overlap again, and it looks like the SN2 is going to be our predominant fast reaction here. We're going to draw our arrow from our negative charge to this electrophilic carbon on this primary alkyl halide in an SN2 reaction, and that's going to kick off this bromine leaving group. What's that going to give us? That is going to give us this oxygen, which is now bonded to 2 other carbons, and we have an ether as our final product in this reaction. Once again, there's nothing particularly new in this reaction. What we have is first an acid-base reaction where we're simply deprotonating the oxygen, and that leaves behind a strong nucleophile. We can use that strong nucleophile in an SN2 reaction, which is what we did here. The last thing we usually talk about when it comes to alcohols is that when you have a primary or a secondary alcohol, we can oxidize the carbon bonded to the oxygen. Sometimes oxidation is covered in organic chemistry before the chapter on alcohols. Sometimes your first introduction to oxidation is on alcohols. So if that's the case, for review, oxidation in organic chemistry can be described by one or both of the following scenarios. One, we're increasing the number of C-Z bonds in a molecule, where Z is an atom more electronegative than carbon. And, true to its name, Z is usually oxygen in oxidation. Second, we also say that oxidation can be decreasing the number of carbon-hydrogen bonds. Now, when it comes to alcohols, there must be at least one hydrogen bonded to the alpha carbon of the alcohol for it to be oxidized. That is, only primary and secondary alcohols can be oxidized. One of the most important things that I can tell you about oxidation is that you need to know your oxidizing agents. And there are weak and strong oxidizing agents of alcohols. The weak oxidizing agents, you have 3 of them, are HCrO4 amberlist A26 resin, PCC with CH2Cl2, and DMP. Some organic chemistry classes focus on PCC only, but I've seen others that also mention the HCrO4 amberlist A26 resin, and yet again I've seen others that have DMP. Now, when it comes to PCC and DMP, here are some pictures of what they look like. So you can see that PCC is pyridinium chlorochromate, and it's really just an ionic compound, which I have the visual representation of it as well as the chemical formula of it. And DMP is des-Martin periodinane, and it's this giant molecule here, which is why we use the abbreviation. Now, your strong oxidizing agents, you can either use CrO3 or Cr2O7 2-. Now, usually that's accompanied by Na2 or K2 to balance out that negative charge, so it's an ionic compound. And whether you use the CrO3 or the Cr2O7 2-, it needs to be with acid, so we add H2O and H2SO4 to make that oxidizing agent work. We also have KMNO4 as our other strong oxidizing agent. Like I said, it's very important to learn your oxidizing agents and learn which ones are weak and which ones are strong. Now, beyond that, knowing what a weak oxidizing agent does and knowing what a strong oxidizing agent does is your next step. Rather than learning specific oxidation mechanisms, which can often be pretty complicated, It's more practical to know that weak oxidizing agents will oxidize alcohols one time only, and that strong oxidizing agents will oxidize alcohols as many times as possible. So let's take a look at our oxidation reactions. We're going to start with a primary alcohol. You can see that I drew that on the left, and I drew the hydrogens bonded to that alpha carbon in blue. Normally we don't show hydrogens, but I wanted to show you that primary alcohols can be oxidized up to 2 times because of those 2 hydrogens bonded to that alpha carbon. When reacting a primary alcohol with a weak oxidizing agent, or in other words one from the list on the previous slide, all we're going to do is we're going to remove one alpha hydrogen and turn the COH into a C double bond O. So by definition with oxidation, we can decrease CH by 1 and increase CO by 1. So a weak oxidizing agent will oxidize once. So once again, we're getting rid of one of those CH bonds and we're replacing the COH bond with a C double bond O. This reaction, of course, yields us an aldehyde product, which we normally draw the hydrogen on aldehydes, so I'm going to draw it on there. Now, when reacting a primary alcohol with a strong oxidizing agent, we're going to remove both alpha hydrogens because we're going to completely oxidize the alcohol. So we replace both carbon-hydrogen bonds with a carbon-oxygen double bond. So in other words, we have a double bond O and an OH now. So we decreased CH by 2 and increased CO by 2, and this yields a carboxylic acid product. Next, we're going to look at secondary alcohols. Now, in a secondary alcohol, we can only oxidize them one time because there's only one hydrogen bonded to the alpha carbon. So when we react a secondary alcohol with either a weak or a strong oxidizing agent, we're going to remove the sole alpha hydrogen and turn the COH into a C double bond O. So in other words, since we can only oxidize once, a weak oxidizing agent will do just that, and a strong oxidizing agent has no choice but to do it just one time. So we're decreasing CH by 1 and increasing CO by 1. This, of course, yields a ketone product. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.